Hello everyone. In this video, we're going to walk through 3 examples of how to determine arc length of a polar curve. In our first problem, we have r equals e raised to the 3 theta, and we want to determine the arc length of that curve from 0 to 2 radians. So we could always graph it on our calculator just to see what it looks like and get a better sense of what length we're actually trying to find. Being in polar mode, we'll go ahead and graph e to the 3 theta. We can try zoom 6 to start. And if we go under window, remember we do want to find the arc length from 0 to 2 radians. It looks like when we did zoom 6, it set it up from 0 to 2 pi. So we could change this to 2. And let's graph it from there, see what it looks like. Same shape. We don't really see the end of it. Let's start tracing and see how far we have to go. When you hit trace, you'll notice at the bottom, we're starting at a theta of 0, and it tells us the x and y coordinates at which we're located right now. So if we just start going off to the right, you can see I'm almost at a theta value of 1 radian. See how high up this y value goes. Oh, really high up. So we'd have to change our window pretty big to accommodate a large y value such as that when theta is almost 2 radians. But now at least we know what length we're looking for. So returning to the problem, remember that we do have a formula to determine the arc length of a polar curve. That formula states that the length of the polar curve from alpha to beta is going to be the square root of r squared, so we have r, and then we have to find dr d theta, so we will need to do that part, and we need to square that as well. So that's the formula we're going to be using in all of these problems. Let's go ahead and find the dr d theta that we're going to need. Using chain rule, we'd have e raised to the 3 theta, but then we need to multiply by the 3 that is the derivative of the exponent. Substituting in, we're finding the integral from 0 to 2 of the square root of r, that quantity squared. And now we have to square that derivative that we found as well. From here, we're simply going to evaluate it in our calculator. So let's go take a look at how to do that. I'm assuming you're in polar mode, having just graphed this function. Your calculator's really not going to care whether you're in polar mode, regular rectangular function mode. It's going to calculate the integral the same way. The one part that does matter is that you're in radian mode. But you should be for calculus anyway. But just to make a note about that. So if you return to your quit screen, we'll do math 9 from 0 to 2 of the square root, and now we just have to make sure we type everything in correctly. So we have the quantity of e raised to the 3 theta, and close your parenthesis, and you have to square that. And we have plus, and now we need the derivative we found, so that was 3e raised to the 3 theta, and close that parenthesis and square it. So just take a good look at it and make sure you typed it in properly. And hit enter. And we get a rather long arc length, which makes sense given that we knew that point when theta equaled almost 2 was up around a y value of 300 some. So kind of makes sense. So let's go take a look at another one. In this one, we have the polar curve 1 plus cosine theta, and they simply want us to find the arc length in the first quadrant, so thereby implying that we're going 0 to pi over 2. So we can take a look at this one as well on our graphing calculator. Returning to our function values, we have r equals 1 plus cosine of theta. Let's go ahead and do zoom 6. So we have here a nice cardioid. If we do zoom trig, I wonder if that allows us to, there's a little bit better. Definitely a cardioid with the little dimple here on the left. And we want in the first quadrant, so 0 to pi over 2. So let's find dr d theta, because as we saw from the formula, we do need that calculation first. So the derivative of this simply is negative sine of theta. So setting it up, we'd have the arc length is going to go from 0 to pi over 2 of the square root, square the r value, plus the r d theta squared. And we once again will be utilizing our calculators to find this. Returning to our quit screen, we once again have math 9, 0 to pi over 2 of the square root of the quantity 1 plus cosine theta. So remember that first parenthesis closes the theta, then you need another one to close the quantity before you square it. And then we have plus the quantity negative sine theta squared. So looks like that, theta on the end. And you should obtain approximately 2.828. In our last example, we're simply asked to find the arc lengths of r equals 2 sine 2 theta, thereby implying that we want the entire arc length. So let's take a look at it first so we know what it is we're trying to find. Let's clear out what we had for R1, and we have 2 sine of 2 theta. Let's try zoom trig to start. We get a nice rose. So finding the arc length, since they did not give us bounds otherwise, we're essentially trying to find the entire perimeter, if you think of it that way. Now, one thing you do have to be careful about, though, is that you do have to play a little bit with your window just to ensure that with the values you have, especially for theta, that you're not tracing over the curve twice. So let me show you what I mean. Notice here when we did zoom trig, it automatically sets it up from a theta value of 0 to 2 pi. If we were to change the theta max simply to pi instead of 2 pi, and then graph it, notice how we only get the right side of the rose. So the rose is not yet complete. You do not have a complete graph yet. If we go back and make it 2 pi as it was, graph, now we have the full curve. Sometimes, depending upon the equation, even going to 2 pi, it ends up tracing over itself. And that's what you don't want, because then you end up essentially double counting the arc length when you find it. So you really do have to be careful when they do not give you the limits of integration and you are left to find them yourself. You need to make sure you're not double counting and tracing over the curve. You're going to see this as we talk about area of polar curves as well. So for this, we do want to use 0 to 2 pi as the limits of integration. So let's find dr d theta that we'll need. Once again, it's a chain rule problem, so we'd have 2 times cosine of 2 theta, then we need to multiply by another 2. So we end up with 4 cosine of 2 theta. So as we just saw, we do want to go 0 to 2 pi with our limits of integration. We're going to square the r function, square dr d theta, and that's what we're going to evaluate on our graphing calculator. Please note that you will be able to do it that way on the AP exam as well. You would not be expected to do this by hand. You would have to show what we have shown here in terms of setting up the integral, but it is assumed from that point you'll go ahead and evaluate it on your graphing calculator. Returning to our quit screen, let me clear some of this out. We'd have math 9, 0 to 2 pi, as we just determined, square root of, we have 2 sine 2 theta, that quantity squared. Again, watch your parentheses. So you need one parenthesis to close out the 2 theta, then your other one before you square it. Plus, now we need dr d theta squared. So that was 4 cosine of 2 theta. It looks like that. And then your d theta on the end. And as I mentioned before, if by chance you're in rectangular regular function y equals mode, and when you're doing this you have x's, you are going to get the same answer, right? As I noted, the important part is that you are in radian mode instead of degree mode. And we obtain 19.377 approximately for our final answer. So think of that. Remember what the graph looked like. That's pretty much like the perimeter around the entire curve. So hopefully these examples will help you get on your way to try some on your own.